तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, this will be lecture number 18 on the ongoing series on mechanical measurements. Towards the last lecture, end of the last lecture, we were looking at pyrometry. We briefly considered the nature of the black body radiation, and we just had enough time to discuss or mention about two concepts, the brightness temperature and the color temperature. So, what we will do in this lecture is to continue from where we left off, introduce these terminologies like the brightness and color temperatures, and indicate how these can be used for measuring high temperatures, specifically surface temperature of bodies at high temperatures. When I say high temperatures, we are talking about the temperatures greater than about the silver point or the gold point. These are already familiar to us from our discussion on the international temperature scale of 90. To just recapitulate, we go over again some of the basic concepts. The first one is the concept of the black body, whose spectral emissive power depends on the wavelength lambda and the temperature T. And as I indicated earlier, the black body emissive power in watts per square meter micrometer is a unique function of wavelength as well as the temperature. So, if I fix the wavelength, for example, if I fix the wavelength, then it becomes a unique function only of temperature. So, that is the basic idea of using this equation as a basis for thermometry in what is called a pyrometer. So, let us look at some of the details. We have already done this earlier. I have taken an example of I have plotted the monochromatic emissive power as a function of temperature, and just recapitulate what I said a while ago. We will fix the wavelength at some particular value. So, you see that the value is given by this vertical line, the red line which is shown here, the vertical line. The color of the line is red because this is in the red region of the electromagnetic spectrum. It is in the visible part of the spectrum. You can see here this 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, between 0.6 and 0.7 micrometer. The value which I have shown is actually used in pyrometer. And if you go up on this line, you see that there is a unique temperature variation of the monochromatic emissive power as a function of temperature. As you increase the temperature, the intensity or the value on the y axis is going up, and it is going up by orders of magnitude. And here I have taken examples, first one being at 1500, the second one is 5800, and these have been chosen specifically because the 5800 is roughly the upper limit up to which I am going to use the pyrometer. So, the point to notice is that there is a unique relationship between the y axis here, which is QB lambda, and the temperature once I fix the wavelength at a particular value. What we normally do in practice is, because in the Planck distribution function, if you go back and look at it, in the denominator I have e to the power of C2 by lambda t, where C2 is the second radiation constant, which has a value of about 14,000 and odd. So, this is a large number, and you see that if lambda times t product, typically for example lambda equal to 0.5 or 0.6 micrometer, even if we take temperature of the order of 5,000 or 6,000, which we talked about as the solar temperature, you see that this lambda T product will be 0.6 times 6000, about 3600, C2 is about 14,400, and therefore 14,400 divided by this will be 0.6 into 6, 3600. It is a factor of e to the power of 4 or 5, and this factor is much larger than the factor 1 here. Therefore, sometimes what we do is, especially for the sake of considering a parameter measurement of temperature, we will ignore this factor -1, and that is called the Wein's approximation to the black body function, and that is what I have given here. So, the Wein's approximation says that we can ignore the factor -1 in the denominator. The difference between the Planck function and this function is only that I have neglected the -1 in the denominator. So, QB lambda T equal to C1 by lambda to the power of 5, 1 over e to the power of C2 by lambda T, and if I fix the value of lambda, this is a fixed value, C1 is a constant, C2 is a constant, lambda is fixed. You see that QB is proportional, is equal to some constant divided by e to the power of some constant divided by T. So, there is a definite relationship between QB lambda and the temperature. Let us look at the error which is committed by using the Wein's approximation instead of the Planck function. You notice that I am going to neglect that -1 factor in the denominator as compared to e to the power of C2 by lambda T, and for the kind of values here I have taken from 0 to 5000 Kelvin, which is the normal range we are going to be interested in practice. You see that the maximum error in using the Wein's approximation as compared to the Planck function is only about 1%, and this is small enough to be of no concern to us. Therefore, we will assume that for the purpose of pyrometry I can use the Wein's approximation, and therefore that simplifies the calculations a little bit, even though there is nothing wrong in using the full Planck function. And here I have, you should notice that I have used 0.65 micrometer as the fixed value for the wavelength. So, the thermometer which uses the black body function fixes the wavelength at a particular value and makes the black body function a function of temperature alone, and that is the basis for thermometry. So, let us look at the source of black body radiation, because in laboratory if you want to calibrate a parameter, I must have a source of radiation which is a black body. The normal way of making or obtaining black body radiation is to use what is called a cavity furnace. So, the cavity furnace consists of, you see here this black thing is electrically heated, a refractory sphere something like 0.3 meter diameter, and this sphere is placed in a box with the insulation here, so that the heat loss from the sides of the spherical cavity is reduced. We also have a temperature controller which will adjust the heat input to the electrical heaters such that the temperature is fixed or kept fixed at a particular value we want, and the temperature is sensed by a sensor which is attached to the wall of the electrically heated sphere. And there is a narrow opening of 50 millimeter diameter, as you have shown here, 50 millimeter diameter opening with a 150 millimeter diameter some kind of a tube attached to it, and the radiation which is leaving from the sphere through this opening to the outside approximates black body radiation very closely. And sometimes what is done is, behind the heated sphere I can also have a phase change taking place in a material of given melting point. For example, I can have the cavity, behind the cavity I have a receptacle or an enclosure in which I am going to have a metal which is going to be allowed to undergo a phase change, that means it is going to melt. You start from a low temperature, approach the temperature of melting, so the material starts melting. During the process in which it is melting, when the material is present both in the form of solid and the liquid, you will have a constant temperature. That constant temperature is nothing but the liquidus temperature of the substance, and the cavity will be exactly at that temperature, and therefore the black body will give you black body radiation corresponding to the melting temperature of the solid which is undergoing a phase change. In fact, we can choose different materials with different melting points, so that the black body can operate at constant temperatures during the time it is undergoing this melting process. It will be at a constant temperature, and therefore, I can have different temperatures achieved. For example, gold point, you can have gold which is melting, or you can have the silver point, the zinc point, lead point, and so on, depending on the material you have chosen. The radiator characteristic of the cavity is shown here, and in fact, if you remember what I said, I have a large spherical cavity here. This is a large spherical cavity of 0.3 meter diameter with a small hole on the side. So, the opening has an area of the pi d squared by 4, pi into 50 square millimeters, 50 millimeter square divided by 4, that is the area, whereas the surface area of the sphere is pi d squared and 0.3 meter diameter. You can see that it is a very large area compared to the area of the opening. What I have done in the next slide is to show what happens to the effective emissivity of the radiation coming from the opening. Emissivity is something which tells me how close is the radiation to that of black body radiation. If the emissivity is very small, that means that the radiation coming out from that opening is not at all like black body radiation. If it is very small, it is not like black body. If it is very close to 1, it is like black body radiation. Therefore, what we want to have is a black body radiation coming out of the hole, because that is the basis for thermometry. Therefore, what I should do is, I should have a ratio of opening area to cavity surface area as small as possible, number 1. Number 2, I must choose the surface to have essentially a very large emissivity to start with. Different surfaces have different emissivities. That means that if you have two surfaces, one black surface and one surface which is not black, if you heat them to the same temperature, the black surface will give you a heat, will emit radiation according to the Planck distribution function full amount, whereas if the surface is not black, it has got, let us say, it emits a fraction of that emitted by a black body at the same temperature. That fraction we call as the emissivity. So, remembering that emissivity is a property of the surface, if I have a cavity whose surface already has a high enough emissivity, in this case I have taken a cavity surface which has got an emissivity of 0.95, and if I make the opening very small compared to that, for example, I can have an opening 1 over less than 10%, less than 5% of the area of the surface of that sphere, then you can see that I am approaching the emissivity equal to 1, that means it is approaching the black body radiation. Therefore, the requirement of a furnace or the black body cavity furnace is that you have a very large area for this surface of that cavity, let it have as high an emissivity as possible to start with, and then make this opening as small as possible. Of course, if you make the opening very small, the amount of radiation coming out will be small, but there is a part of the price we pay for getting or approximating the black body characteristic very closely. So, what comes out of this hole, if you have a very narrow hole compared to the size of the cavity, is black body radiation. So, the black body radiation will be used basically as a calibration. Now, let us look at we go back to what we showed earlier. If you fix the wavelength at a particular value, we know that the brightness, the amount of radiation coming from the surface is a function of temperature given by the Wien's displacement, Wien's law now instead of the Planck's law, because we are approximating. So, the brightness temperature is actually defined such that the emissive power of the actual surface is the same as that of a hypothetical black body at the brightness temperature Tb. Why do we do like this? Suppose the surface in question is not a black surface, we know that it will emit less than a black body at the same temperature. So, I want to now compare it with a black body which is going to emit the same amount, that means it will be at a different temperature, obviously lower than the actual temperature of the body, such that it is going to give the same amount of heat per unit area per unit frequency interval. So, if I fix the lambda constant, if I fix the lambda value by some suitable arrangement, the amount of energy emitted per unit time, per unit area, per unit wavelength interval by the black body is given by QB lambda, which is now at the temperature Tb, which I call as the brightness temperature, which should be exactly equal to the Q A lambda. A stands for the actual surface at the temperature, actual temperature Ta, which is the temperature. In fact, what is my intention? My intention is to know what is this Ta in reference to this Tb. So, if I can get a relationship between Ta and Tb, I will be able to use this method. By measuring Tb, I will be able to find out what is the actual temperature. So, let us look at the calculation of how we are going to do that. So, the brightness temperature simply says that, if you go back to the previous slide, Qa lambda Ta equal to Qb lambda Tb, and let us assume that the actual surface has an epsilon or the emissivity equal to epsilon lambda. This is a fraction less than 1 multiplied by, according to Wien's law, C1 by lambda to the power of 5 e to the power of minus C2 by lambda Ta. This is the Qa lambda. What is given here? This is Qa lambda. This must be equal to Qb lambda at Tb. So, Qb lambda at Tb, black body, epsilon is 1. So, there is nothing here, there is factor 1, C1 by lambda to the power of 5 e to the power of minus C2 by lambda Tb. Now, notice that C1 by lambda to the power of 5 can be cancelled off from the two sides. Therefore, I have epsilon lambda e to the power of minus C2 by lambda Ta equal to e to the power of minus C2 by lambda Tb. I can take logarithms on the both sides and rearrange to get the equation which is given here. This is called the ideal parametric equation, which says that reciprocal of the actual temperature minus the reciprocal of the brightness temperature equal to lambda by C2. This is coming only from here, lambda by C2 logarithm of epsilon lambda. So, you notice that lambda is fixed, the brightness temperature is obtained by measurement, which we will see how it is done in a little while from now. The actual temperature is what I want. If I know the epsilon lambda, that is, if I know the emissivity is the surface whose temperature I am trying to measure, then I will be able to obtain the actual temperature, knowing the brightness temperature, knowing the value of lambda at which the measurement has been made, knowing the emissivity of the surface. This is basically what we do in pyrometry. So, the pyrometer consists of an instrument which is going to help us in measuring Tb, and if we know epsilon lambda by some means, by some other measurement, then we will be able to use this pyrometry equation to calculate the temperature. It is called the ideal parametric equation because I am using logarithm of epsilon lambda here. Later we will see that we will have to modify that epsilon lambda as an effective emissivity, which will take into account some losses, which we will talk about a little later on. So, the idea is to measure the brightness temperature. The instrument I am going to use for this purpose, for measuring the brightness temperature, is actually a comparator which compares the brightness of two objects. The object whose temperature I want to measure, I want to compare it with a black body whose temperature I can measure or I know. Okay. So, I compare these two and I bring a match between these two. If you remember what we talked about earlier, this is the match we are talking about. The amount of heat coming out per unit area, per unit time must be the same for the two at a given wavelength. So, this match is what we are doing. This match is called, if the two are in match, we say that they are equally bright. That is why the brightness temperature. So, what I do is, I will use an instrument which is shown schematically here. Let me just describe all the parts of this instrument. We have the target whose temperature I want to measure. I have a field lens which will gather light coming from this target, and then it will be focused onto the plane of a filament which is shown here, and the filament is actually run by a battery, a variable resistor, an ammeter, and so on. So, we will come back to this in a little while from now. The radiation coming from the target is made to pass through an aperture, so that stray light is not entering the instrument. It is an optical instrument. Then it passes through a gray filter which will, if necessary, reduce the brightness by a known factor, then it falls on the filament, and now as far as the objective lens is concerned, it receives light which is coming both from the target which has passed through the gray filter, and then it also receives radiation from the filament which is run by this battery. Okay. By variable resistor, varying this resistance here, I can vary the temperature of the filament, and therefore the amount of radiation comes from the filament. So I can, in other words, change the brightness of the filament by changing the variable resistor position. When I change the variable resistor position, the current through the filament is changed, and the current in fact becomes a measure of the brightness of the filament, or it becomes a measure of the temperature of the filament. So, it is usually a tungsten filament which is run by a battery, variable resistor and an ammeter. So, before it is gathered, it is looked at by the eye of the person who is making the measurement. It also passes through both the light gathered from the target as well as from the filament, passes through a red filter. This red filter along with the eye of the person who is looking at it, it has got a certain response to the light which is falling on the retina. So, the two together will help us in finding out or selecting a certain wavelength of operation for this instrument. Okay. So, I am going to look simultaneously at two things: the object whose temperature I want to measure, and I am also going to, or the operator is going to look at also the filament whose brightness I can vary. So, the operator will have to adjust the resistance such that the target and the filament appear equally bright, and which can be verified by making the proper adjustment. For example, if the temperature of the filament is very high, you can see here the filament is appearing bright in a background, red background, which appears to be dull. If you go here, if the temperature of the filament is too small, then you will see that it appears dark, looks like a shadow in the background which is brighter. And in fact, if the adjustment has been made properly, you will see that there is the correct adjustment, then the brightness, the filament and the background are equally bright, there is no contrast between them. So, what happens is that the filament and the background have merged together, the filament has become invisible, and therefore it has vanished, and therefore we say it is a vanishing filament pyrometer. So, in the vanishing filament pyrometer, we make the adjustment of the variable resistor so that the ammeter current is varied, so that you will see that the target and the filament appear equally bright. So, with this basic understanding of this instrument, let us look at some of the features. Suppose the filament, assume that the filament can work at a maximum temperature of, let us say, 3000 degrees Kelvin, okay? Because the filament cannot operate at any temperature you want, it has got a limitation. If it goes beyond some particular value, the filament will melt, and you will have to replace the filament. So, the filament has a maximum temperature up to which it can go, and therefore, theoretically the maximum brightness temperature I can measure using this filament is the maximum temperature of the filament itself. Okay. Therefore, if the target is at a temperature higher than the filament temperature, what I am going to do is I am going to use a gray filter which will reduce the intensity by a factor which can be calibrated, or a known factor. So, in other words, I can reduce the amount of radiation which is coming from the target by using this gray filter, and reduce it by a fraction, known fraction, for example half or 1/4 or 1/8 and so on, so that the intensity of light which is coming from the target is equal to or less than the maximum, the intensity of the filament at the maximum of its temperature. In other words, I am going to choose the range of the instrument by using the gray filter of desired transmittivity. If you go back now to the ideal pyrometry equation, we had lambda by C2 ln epsilon lambda equal to 1 over Ta minus 1 over Tb. Now, the effective emissivity will be nothing but epsilon lambda multiplied by, because we are going to put a gray filter, it is going to reduce the intensity, it is like multiplying this by a factor, the factor equal to half or 1/4 or 1/8 and so on. So, I will say that this epsilon lambda will be nothing but the actual emissivity of the surface multiplied by the fraction which is allowed to get into the instrument. And in fact, we can also account for other losses, like for example, in the case of the vanishing filament pyrometer, there are so many surfaces. There is a lens here, the front surface, the back surface, the gray filter, the front and back surface and so on. At each surface some amount of reflection will take place. Therefore, it is like actually like a loss as far as the amount of radiation which is coming into the instrument is concerned. Therefore, we can club together all these factors into what is called a transmittivity or a transmittance, and we can say that in this equation epsilon lambda is actually the emissivity of the target multiplied by the transmittivity of the optical train. So, if we do that, this epsilon lambda will be called the effective emissivity instead of the actual emissivity of the target. Second point, suppose I do the following. Suppose I keep the filament at a constant temperature. I adjust the factor in this gray filter. If I have a variable filter with various filtering coefficients or various fractions which I can allow, then I can adjust the gray filter alone without adjusting the ammeter at all. Just keep the ammeter at a particular value which you choose, so that it is at a given temperature. For example, it may be maintained at the gold point temperature, for example. Then by simply adjusting the gray filter, I will be able to bring a match between the target and the filament. So, in this arrangement, what is going to happen is that the filament is going to operate all the time at the same temperature, and therefore, theoretically its life will be increased. Number one, from the point of view of the operation of the filament itself, it is very good, because you are not subjecting it to cycling in temperature. The second point is, I am going to have a fixed reference temperature, the gold point temperature here as the reference point, with which I am going to calibrate the temperature of the target. Therefore, just by varying the factor epsilon lambda or the effective emissivity of the target, by changing the fraction which is allowed by the gray filter to pass through, I will be able to do the thermometry by using a single temperature of the filament, which can be chosen as the gold point or the silver point or whatever you would like to have, which is usually at a temperature which is much lower than, which is low enough for the filament to last for a long time. That is one way of doing it. That means that we are bringing back the idea of having a single fixed temperature as a part of the thermometry or the ITS 90. So, that is the advantage of that. So, two ways of operating the instrument. One is of course to have filament run at different temperatures, and in fact the temperature of the filament, it becomes the brightness temperature, and in the pyrometry equation this will keep on changing. Then we use this to measure the temperature of the actual surface. In the second arrangement, I am going to keep this constant, I am going to vary this portion. So, in other words, the pyrometer can be used in two ways. One is keeping the right hand side constant and working with the variation in this factor here, or you can keep this constant and work with the change in the right hand side. So, these are the two ways of using the pyrometer, and the second way is in fact more satisfactory from the point of view, from the theoretical point of view also, because we are going to have a single fixed temperature as a reference for thermometry. So, now just to complete our discussion on the vanishing filament pyrometer, I said that we are going to choose the particular wavelength by the combination of the red filter and the eye, and that is explained in the graph here. The eye response of a typical person is like this: the transmittance versus wavelength for the red filter, or in the case of eye response, you just replace this transmittance by the response of the eye for different wavelengths, and you see that our vision has got this kind of a response, and the red filter will cut off everything above certain wavelength. So, below that it will transmit nothing, and above that it will transmit almost like 90% here. Okay, it is a short cutoff here. Below this it is not going to allow anything. Therefore, if you look at the product of these two functions here, and that is in fact this is something proportional to this triangle I have shown here. The radiation which is allowed to enter the eye is basically this portion, which is roughly at 0.65 micrometers centered, and a small window around that. So this is the reason, this is how you are going to fix the lambda in the case of the vanishing filament parameter. Let us look at a few of the characteristics which can be derived from the ideal parametric equation. For example, if I vary the emissivity, what happens to brightness temperature? Suppose I take an object at 1500 Kelvin and I just find out what is the effect of the emissivity. You can see that between 0.7 and 0.76 I have varied, more or less there is a linear variation, and you can see that between 0.7 and 0.76 it varies between 1465 and about 1473 or so. Okay. So 65 and 73, about 8 or 9 degrees variation will be there. So it is not all that sensitive within small. In other words, I can allow some amount of error in the emissivity without compromising the accuracy of the measurement. This is easily derived from the parametric equation. Suppose I take the brightness temperature as a function of emissivity I want to see. Suppose the actual temperature is 1000 Kelvin, 2000 Kelvin. You can see that if the emissivity is very low, like 0.1, the brightness temperature of the object at 2000 Kelvin is only 1600. You will notice here that the brightness temperature is always less than or equal to the actual temperature. When epsilon becomes 1, the brightness temperature and the actual temperature become exactly equal to each other, because 1 over Ta minus 1 over Tb equal to whatever is on the left hand side. If you put epsilon lambda equal to 1, logarithm of 1 is equal to 0, so the right hand side becomes 0, and therefore the brightness temperature and the actual temperature are the same. This is after all a definition. A black body should have a brightness temperature equal to its own actual temperature. Any other surface will have a temperature, brightness temperature lower than that of a black body. Okay, that is what is clear from this. I have taken two examples, one at 1000 Kelvin, the other at 2000 Kelvin. Suppose I do the following experiment. This is the brightness temperature I am keeping constant equal to the gold point, 37.6 Kelvin. If you remember from our ITS 90, this is the temperature of the gold, melting gold, and I am taking lambda equal to 0.66 micrometer as in the case of a vanishing filament parameter. Then if I keep this constant with different emissivities, you can see a surface with emissivity of 0.2 requires to be almost at 1500 Kelvin to be in match with the gold point temperature. However, if you go almost up to 1, very close to 1, you see that the temperature will match exactly. The actual temperature and the gold point temperature are going to be more or less the same. Therefore, this will give you some kind of an idea as to what is going to happen to the difference between the actual temperature and the brightness temperature. In practice, we also require some idea about the emissivity values of various surfaces, and there is no best way of doing it. Most of the times what one has to do is to, if you are going to use a parameter regularly in your particular application, it is better to do a set of experiments such that the emissivity is known for a particular surface which you are going to use in your application. Make a calibration of the emissivity of the surface so that you can use that. That is the best method. However, just as a guide, I have given some values which are taken from the references. The surface temperature is given here, 600, 1200, etc. These are the approximate emissivity values which are given. For example, iron can vary between 0.2 and 0.37, between 600 and 1200. If it is unoxidized, if it is oxidized, you can see that it changes quite drastically to 0.85 and 0.89. And if you take molten cast iron, 0.29, molten steel 0.28, and nickel 0.75. Fire clay, this is very common in furnace practice. We use fire clay as the surface material for the furnace, 0.52 and 0.45. Silica bricks again 0.54 and 0.46. These are all high temperature insulating materials. Alumina bricks, for example, 0.23 and 0.19. So, if I am going to measure the temperature of the surface of the brick using a pyrometer, I can use an approximate value of 0.23 for the emissivity and make the measurement. Now, the other question is, we have actually answered this question a little bit earlier also. If the error in emissivity is given, let us say I have taken between 0 and 10%, the error in temperature is something little smaller. So, the percentage error in the temperature is slightly smaller than the percentage error in the emissivity, as you can see from here. All this is derivable using the ideal parametric equation, the pyrometry equation. So, let me take an example and work out the numbers so that it becomes clear as to what we are talking about. So, I have a certain target which has a brightness temperature of 1700 Kelvin when observed by a vanishing filament parameter of the type I just now described. It operates at a wavelength of 0.66 micrometers. So, the emittivity of the object at this wavelength is known to be 0.86. This is given to us. So, we want to find out what is the actual temperature of the object. This is basically an application of the ideal parametric equation. The second part, however, requires a little bit of work. If the emissivity has an uncertainty of plus or minus 0.01 and the brightness temperature has an uncertainty of plus or minus 5 Kelvin, what is the uncertainty in the actual temperature of the target? The second part requires the use of the error propagation formula, which we have discussed earlier. So, we will work out this solution on the board by taking the numbers given in that example. So, we are using this example 19. The first part, I am given the brightness temperature, which is 1700 Kelvin. Lambda is specified as 0.66 micrometer. The emissivity of the target is also specified as 0.86, and we know that the second radiation constant C2 is 14,390 micrometer Kelvin. So, these are the data given. So, all I have to make use of the ideal parametric equation, 1 over Ta minus 1 over Tb equal to lambda by C2 logarithm of epsilon lambda. We are making the assumption this is the effective emissivity. Because it is not specified, we can simply assume it to be the effective emissivity. So, I have given all these constants, this is given, this quantity is given, all the other things are known. All I have to do is to obtain the value of Ta. I can rewrite this equation as Ta equal to 1 over Tb plus lambda by C2 logarithm of epsilon lambda, and I can substitute the values 1 over 1700 plus 0.66 divided by 14,390 logarithm of 0.86, and if you work it out, it comes to 1720.2 Kelvin. This 0.2 I can ignore, it is not significant. So, I can simply say 1720 Kelvin. This is the actual temperature of the surface whose brightness temperature is given as 1700 Kelvin, and the effective emissivity of the target is 0.86. The second part requires the calculation of the error. So, the part B, I am given delta epsilon lambda is equal to 0.01, and we are also given that the delta Tb, actually you can say this is plus or minus, again this is plus or minus 5 Kelvin. I would like to find out what is delta Ta, that is the problem which is given to us. So, what I am going to do is I am going to use the following formula. So, we will say the delta T A is equal to plus or minus square root of partial derivative of the expression for T A with respect to T B multiplied by delta T B whole squared plus partial of T A with respect to epsilon lambda multiplied by delta epsilon lambda whole square. So, all I have to do is to calculate, this is known, this quantity is given plus or minus 5 Kelvin, this is given as plus or minus 0.01. I have to obtain the two partial derivatives, and these are also called the influence coefficient. So, I can say that this delta dou T A by dou T B is nothing but the influence coefficient I T B, and this is the I epsilon lambda. So, I have to take the expression which we used in the first part, take the partial derivative, and therefore, I can obtain the following. This will come out to be minus 1 over 1 plus 1 over T B plus lambda by C 2 log epsilon lambda whole squared multiplied by minus 1 over T B squared. So, we substitute the values which are given in the problem, and you can verify this gives you a value equal to 1.024. So, similarly, we work out the other influence coefficient. This is given by epsilon lambda, this is I epsilon lambda, this will be minus again 1 over T B plus lambda by C 2 whole squared multiplied by lambda by C 2 into 1 over epsilon lambda. All I have to do is to substitute all the values, and we will get a value of minus 157.81. So, the two influence coefficients are available to us now. So, I can calculate now the error in the actual temperature as plus or minus square root of 1.024 into 5 whole squared plus, when you are using the error propagation formula, this minus will not come into the picture because it will be all squares of terms. Therefore, this will be 157.81 into 0.01 because there is the error given whole squared, and this works out to be plus or minus 5.4 Kelvin. So, we will say that the temperature estimated of the target is 1720 plus or minus 5.4 Kelvin. So, there is a error bar of plus or minus 5, which is quite acceptable when you are measuring temperatures as large as 1700 Kelvin. It is simply not possible to have a better error specification for this, because this is the nature of the quantity we are measuring. We are measuring a large temperature, and the temperatures of the order of plus or minus 5 is quite acceptable in practical applications. So, this is a typical problem based on the vanishing filament parameter and the concept of the brightness temperature. Now, we look at a second concept, which is called the color or the ratio temperature. In the first case, if you remember, we compared the intensity or the brightness of two objects, and by comparison we said that they share some common temperature, which we call as the brightness temperature. Now, I can also do the following. Suppose I choose two wavelengths, lambda 1 and lambda 2. Suppose I have the ratio of the brightness at these two lambdas for the object whose temperature I want to determine. If I compare this ratio with that of a hypothetical black body, which also has got the same ratio, then I can say that the temperature indicated by the ratio of the black body intensities or black body brightness values at these two wavelengths is going to give you a temperature which is shared by the two. So, this we call as the ratio temperature, because it is the ratio of brightnesses at two values, or the temperature is called the color temperature. Color, because we are going to use two different wavelengths, and if you are using the visible part of the spectrum, lambda 1 lambda 2 will correspond to different colors of the electron, the visible spectrum. So, the definition would be the actual temperature, actual surface is the temperature T A, and the ratio is Q A lambda 1 T A divided by Q A lambda 2 T A, and please remember that at lambda 1 and lambda 2 the object may have different emissivities. It may have an emissivity of epsilon lambda 1 at lambda 1 and epsilon lambda 2 at lambda 2. Whereas, in the case of the black body, epsilon is the same whether it is a temperature, it is a lambda 1 or lambda 2, and therefore, the right hand side is simply the Wien's approximation written for the numerator and the denominator without any epsilon coming into the picture. Whereas, in the left hand side I have got the epsilon will be coming into the picture. Therefore, the ratio of the emissivities also is going to come here, depending on whether the ratio of emissivities at lambda 1 lambda 2 is greater than 1 or less than 1, you may have a Tc which is less than Tb, Ta or greater than Ta. Whereas, in the case of the brightness temperature was always smaller than the actual temperature. Here, because of the nature of the definition of the color temperature, it may be either greater or less than or equal to the actual temperature. Suppose we choose two wavelengths which are very close to each other, lambda 1 and lambda 2 are very close to each other, and suppose that the emissivities of the object or the target at these two temperatures are the same, are very close to each other, then you see that the ratio temperature, the Tc, will be the same as the actual temperature. In fact, that is the reason why we use it as the ratio or color temperature, because we would like to make the ratio temperature equal to the actual temperature by choosing two wavelengths close to each other, so that the emissivity is not strongly varying between these two values, so that you get an equality between the actual and the color temperature. So, that is all the basis to it. So, I have shown this using the same figure which I used earlier for the brightness temperature. I have chosen two colors, one red here, another blue. The blue line corresponds to the blue part of the visible spectrum, red color corresponds to. So, you take the ratios of these two quantities, red here and blue here, similarly red here and blue here. So, the ratio temperature will be characteristic of the black body here or the black body here and so on. That is the basis for the color temperature. Let us look at the some of the details. We will go to the board and make a few derivations we will make, so that we will understand what is going on. So, the basically ratio or color temperature is based on the following: Qa lambda 1, Qa lambda 2, is equal to we are just rewriting what we wrote on the slide there. So, I am equating the ratios, the actual at a temperature Ta and the black body at a color temperature equal to Tc. Okay. So, the left hand side I can write it. So, I will say left hand side the same as the actual is nothing but epsilon lambda 1. I am using the Wien's approximation multiplied by C1 by lambda to the power of 5, lambda 1 to the power of 5, e to the power of minus C2 divided by lambda 1 TA divided by epsilon lambda 2 again C1 by lambda 2 to the power of 5 e to the power of minus C2 divided by lambda 2 TA. So, the C1 can be dispensed with. So, this will become actually ratio epsilon, instead of lambda 1 I will just say epsilon 1 by epsilon 2, so that it is easier to write it, multiplied by lambda 2 by lambda 1 to the power of 5. This e to the power of, I can write it as minus C2 by lambda 1 minus plus C2 by lambda 2 multiplied by 1 over T. Okay. So, the left hand side is simply given by this quantity. What about the right hand side? The right hand side is given by the same quantity. If I replace TA by TC, and I will put epsilon 1 by epsilon 2 equal to 1, that is all what I have to do. So, that means that this factor will be there, this factor will become 1 and this will become 1 over Tc. So, let me write it in the next. So, the right hand side will be nothing but epsilon 1 by epsilon 2 is now equal to 1. So, lambda 2 by lambda 1 to the power of 5 exponential of minus C2 by lambda 1 lambda 2. So, I will just write it lambda 2 lambda 1 and lambda 2. So, this will be lambda 1 plus C2 by lambda 2 into 1 over Tc. So, if I equate the left hand side to the right hand side and manipulate the two sides, I will be able to get several expressions which will be useful in practice. So, this slide shows the ratio of the actual temperature to the color temperature, and it can be shown by following the argument which I gave on the board, 1 over 1 plus logarithm of the ratio of the emissivities epsilon lambda 1 epsilon lambda 2 divided by logarithm of the black body function at lambda 1 multiplied by lambda 2 to the power of 5 divided by black body function at lambda 2 multiplied by lambda 1 to the power of 5. And if you remember the definition of the color temperature, this ratio is the same as this ratio. Therefore, I can replace this by this at the actual temperature of the body. This is the ratio at the color temperature, this is the ratio at the actual temperature, these are the same. Another way of recasting these equations is to write the equation in the following form, because this is what is going to be useful for pyrometry or the two color pyrometry, because we are using two different wavelengths. Ta equal to C2 divided by 1 over lambda 2 minus 1 over lambda 1, this is the numerator, divided by logarithm of Qa lambda 1 divided by Qa lambda 2. These are actually measured the brightness of the object at the wavelength equal to lambda 1 at wavelength equal to lambda 2, this ratio. Lambda 1 by lambda 2 whole to the power of 5, these are the two wavelengths we already know, and epsilon lambda 2 epsilon lambda 1 is also supposed to be known. So, in practice, when we are using a parameter or a two color parameter, I am actually measuring this quantity. This Qa lambda 1 by Qa lambda 2 is actually measured, and the rest of the things are known. Epsilon lambda 2 epsilon lambda 1 are known, lambda 1 lambda 2 are specified wavelengths at which we are going to make the measurement. So, everything is known, this is known, then the actual temperature can be calculated using this. So, this is basically what the pyrometer does. We are not as such interested in the color temperature. What we are interested in is in the actual temperature, which can be obtained by the measurement. The measurement we are going to make is the ratio of the brightnesses at two different wavelengths for the same target. So, one way of doing it is to use a two color pyrometer, and it consists of the hot target from which I am going to take the radiation coming out. I am going to collect the radiation using the objective lens, and it falls on a prism, and one part is reflected upwards, the other part is reflected downwards. There are two mirrors which are going to basically give me two beams from the same source. I am getting two beams from the same source, and one of them is going to pass through a red filter. This red filter is different from the red filter we had earlier. This is going to allow a very narrow band around the red value equal to 0.65 plus or minus a little bit. Similarly, a blue filter, and there is in front of that there is a wheel with two holes, or many holes if you want. It is run by a synchronous motor. This is rotating, so it will allow the radiation through this path to pass through this for some time, and after some time it will allow here. Therefore, the photodiode here, or the photo detector here, is going to respond to the radiation coming to the hot target at lambda 1. This photo detector is going to respond to the radiation coming at lambda 2. The blue radiation is lambda 2, red is lambda 1. Then it is going to amplify the signal and then take care of any manipulations, because we have the relation here. I want the ratio of these two, and so on. So, this manipulation can be done by what is called a scalar, and then it is indicated by meter. The indication by the meter is the actual temperature. So, what the two color pyrometer does is to take two beams of radiation coming from the same source, and one passes through the red filter, the other passes through the blue filter, takes the ratio of these two brightnesses, and then gives you the temperature directly. So, what we will do in the next lecture is to consider example number 20, which we are not able to do now. We will work it out, and then once we have done, we will try to look at a new topic, because thermometry more or less we are going to complete here. I may touch upon a little bit on the measurement of gas temperature just to give a flavor, but we will not go deeply into it because it requires advanced knowledge. So, what I will do is I will just touch upon temperature measurement of gases, and then take a look at measurement of other quantities. Thank you.